Okay, so yes, today I will tell you about how we can build a neural network, artificial neural network, that are fully with spintronic devices, and in particular, radio frequency spintronic devices. So I think most of you here are now familiar with the rationale of why we want to build this physical artificial neural network. Well, this is because we have this incredible algorithm called artificial neural networks that have enabled really a revolution in AI these last years, but these are all software that are maladapted to conventional von Neumann computers, and so there's a large push to be able to really find hardware that would be more energy efficient to have neural networks. And because it's really hard to compare what, to have like one same task for the brain and for artificial neural networks, I like to compare things more in terms of at equal energy. So here is an example. So we have GPT-3. So GPT-3 was until last year the most powerful neural networks in the world. So if you have seen news such as an AI wrote a newspaper article, or like an AI created these images from text, most of the time it would have been GPT-3 that had generated this. So really state-of-the-art AI. But what you see is that the amount of energy that was consumed to train this network, so almost 200,000 kilowatt hours, so this was all done on clusters of graphical cards. So this is what the brain would consume during 1,000 years of lifetime, knowing that actually just a little bit of that energy is spent from the brain for actual computation, and most of it is just regulating our body and things like this. So you see that there's this giant mismatch in terms of energy efficiency, and our hope is that if we take inspiration from the brain, not just at the algorithm level, but at the machine level, so by actually building artificial neural network, we will be able to as well have huge gains in terms of energy efficiency. Okay, so we want to build physical neural networks with physical neurons and synapses. And there are several challenges with this, and I will present them to you and show you how I think that spintronics is really a key technology to solve these problems. So the first challenge is that if you want to have large neural networks and to be resolving state-of-the-art tasks, a neural network needs to be extremely large with up to billions of neurons. So you need every neuron and every synapse to be extremely small. So we want nano devices, which is great for us working with nano devices. So in my talk, to clarify things, I will just expect from neuron the simplest thing you can expect from them, which is to be a nonlinear activation function, okay? And from synapses to be weight that can perform weighted sum. So this is more an AI-inspired approach rather than a purely neuroscience-inspired approach. We can talk more about these differences later. But this is basically the very simplest thing you can expect from neuron and synapses. And in my talk, I will show you how we can do both with radio frequency magnetic tunnel junctions. Okay, so first challenge, to have these individual components. But this is actually just the very first step, and the hardest part comes later. The second challenge is that you need to have multi-layer neural networks. We speak about deep learning because state-of-the-art networks have up to hundreds of layers. So you really need to be able not to have just components, but to stack them into a modular architecture. So this means that you need to have your nano device that outputs some kind of signal that then can be fed to another nano device that can make transformation and so on. So you really need to be able to have this successive transformation of synapses to neurons to synapses to neurons and so on. And this is actually not trivial at all if you have nano devices. Okay, so we really need to have this modular architecture. But this is not so easy when you have nano devices. And therefore, actually this has not already been done. So what you find in the literature, and so these are mostly with memory-based devices because these are more advanced in neuromorphic computing. They are more mature. So you see we have papers like this where you have nanosynapses, several layers, connected by something that is not nano, so either a microcontroller or just like off-the-shelf analog components. Or you have fully nano realization, but you always have nanosynapses feeding into nanoneurons. And you never have nanoneurons that feed into nanosynapse. And the reason for this is that usually the output of your nanoneurons is not something that's very easy to work with. So, for instance, that's the output of spiking nanoneurons in that beautiful paper. So you see the signals are not very clean, and often they will need some kind of reshaping before being able to be fed into synapses. Okay. Third challenge, not only you need to be able to connect the layers together, but you need to connect them in a dense fashion. So in the brain, we have incredible connectivity, up to typically 10,000 neurons connected to one neurons. In AI, it tends to approach this now, but it's still a bit lower. And you see, the brain has solved this problem by being extremely complicated and 3D, okay? And so this is not something that I think anyone really wants to do in electronics, especially that, at least for the short term, we are confined in 2D planes. So it's really a challenge to have this high connectivity, and it's not any kind of connectivity. We need not only short-range connection, but we also need long-range connections, which are hard to achieve. And the connections not only need to be dense, but they need to be tunable. We need to be able to independently tune each connection of the network. And this is an incredible challenge, especially that when we're trying to build a physical neural network, this is not really what physical system want to do. Physical system tends to be usually more naturally like locally connected. So for instance, if you have a spin ice, you will be connected to your nearest neighbors. So people really struggle to have this all-to-all connection. By all-to-all, I mean if I have two sets of neurons, each neuron of one set is connected to every neuron of the other set. So for instance, you see in the famous D-wave architecture, so here it's not really neural network, but it's qubits. And they claim that they have 2,000 qubits, and they do have them. But the thing is that because they are locally connected, if you want to implement all-to-all architecture, you need to have some redundancy, and in the end, you can only have 50 fully connected qubits. So you see that because of this spatial locality, it really reduces things that we can do. So it's a very hard challenge, and as I would say, it's like, yes, also sometimes you can have long-range connections, but just because you have a connection doesn't mean that it's easy to tune it. And just because you can tune something locally doesn't mean that you can tune all connections independently. So this is actually something that's really hard, and here, so this is always having this all-to-all long-range connection that are dense and independently tunable is really one of the biggest challenges in the field. Okay, so I want to bring here some answers to this and to show you how spintronic devices can solve many of these problems. So in this talk, I will show you how we have built very small but multi-layer neural networks, where you have successive layers of nanoneurons and nanosynapses that feed into each other, and how we propose an architecture that is modular and that can allow for a dense connectivity. And so I will show you a small experimental realization and then some simulations of larger tasks. Okay, so to really set things straight from the beginning, I will be using in this talk radiofrequency magnetic tunnel junctions, both as the neurons and the synapses. So this is really the same devices that actually came from the same batches that we had in the lab. And so the neuron will be performing a nonlinear activation function. I will come back to how it does it. And it will perform a DC to RF conversion. And then, so it's an oscillator, and the synapses will be resonators that perform this weighted sum by doing an RF to DC conversion. Okay, I will explain how each device does this. But what is important also to notice here that I'm using these spin-torque magnetic tunnel junctions, but this is not about this. We're using these devices, but it could be other devices. What really matters is this oscillator-resonator pair. And so it could be done with many other pairs, and so to link it with the main theme of this conference, maybe it can be done with antiferromagnets. So I'm not the expert in antiferromagnets, but if you guys have some ideas, we can discuss. It could be, of course, it could be much faster if done with antiferromagnets. Okay, so why did we choose the magnetitarian junction? Just because it's a device that's quite mature already, so we can really do a lot of things with them. So for those who might not know, it's multi-layer devices with 2 magnetic layers, and you can both control the magnetization dynamics for spin torque electrically, and you can also read it electrically with magnetoresistance. And so these devices are already quite mature, and so you can already buy chips where they are co-integrated with CMOS in a billion devices as MRAMs. And compared to, so I think here everyone is sold on spintronics, but compared to other nano devices such as memory-safe technology, the huge advantage that we have is that we have a much higher reproducibility and a much higher endurance of the device, because we are doing purely physical phenomena. When you turn the magnetization, you're not damaging the devices. And so we have really a higher reproducibility, higher cyclability, higher predictability compared to other technologies. So this is kind of arguments that you can give memory store people if you meet them. Okay, so first, let's see how we do synapses with these devices. So we are going to use them as radio frequency synapses, which means that the input of the synapse is a radio frequency signal. So here what happens, you send an RF signal through the device. Okay, so your input is the power, the RF power. And what happens actually is that you have this spin diode effect. So when the input frequency of the signal is close to the resonance frequency of the device, you get a resonance. So you see here, I measure the voltage, I measure this DC voltage versus the input frequency, and you see I get this resonance typical anti-Lorentzian shape. Okay, so this is a rectify effect. You can compute this and convince yourself that you will get indeed a DC voltage that's rectified if you inject an RF signal in the junction. So you see we have this resonance curve. And if I put a higher power, I will get a higher signal that is quite intuitive. And I will show you that actually this does a multiplication. So the output is the DC voltage, the input is the RF power, and the output is the input times a weight. And this weight can be controlled by the frequency of the device. So this is our synapse. Okay, so let's see it a bit more in detail. So here I have my resonance, and I decide to measure at this fixed input frequency, here 346 megahertz, okay? And you see if I measure voltage versus power, I get this linear dependence, okay? The dots are the experiments, and the dashed line is my linear fit, okay? So this is indeed a multiplication. And the slope is the synaptic weight. And you see here I have a positive weight, and actually we can see that this, slope is proportional to the difference between the input frequency and the resonance frequency. See, the resonance frequency is here. So now I will change the resonance frequency. So you see now, if I measure here, I will get a negative slope. I have a negative weight because now my resonance frequency is higher than the input frequency. Okay? And if I tune continuously the frequency, so you see here I'm shifting the frequency of the device, I can get continuous tuning of the synaptic weight. And what is very cool with this thing is that you can have both a positive and negative weights in the same device, which is something that you cannot achieve with actually most other nanosynapses. Okay, so here I have told you, oh, we change the frequency of a device. How do we actually do this? So in what I will show you today, we use a dirty experimental trick, which is to have a magnetic, to generate a local magnetic field by having a strip line on top of a device. So we send some current, you get an Ørsted field, and you can modify the resonance. So in these devices, there were vortex magnetitarian junctions, so you can modify the frequency of a vortex by punning with Ørsted field. But this is obviously not what you would want to do in a real system because you see here it's volatile. You need to send some DC current, okay? So what we want to do and what we are actually working on showing now is how to use a non-volatile control. And this has already been shown that you can modify in a non-volatile way the frequency of a device in this paper by putting a memristive material on top, okay? But in the talk of today, we use this Ørsted field. Okay, so now that I have one synapse that does a multiplication, now I want to have several synapses that can do a weighted sum. So because my outputs are voltages, if I want to sum voltages, the easiest thing is just to put the components in series. Okay, so you see here, I put two devices connected in series, and you see now if I measure the voltage versus the input frequency, you see I have these two resonances. So each resonance is one device, and I can also tune their frequencies with strip lines, and you see I can also have different synaptic weights for the device. And so what is important, you see, I measure, if I want to address one synapse, I send the input at different frequency. To see it in a kind of crude intuitive way, it's like each synapse is responsible for a small portion of a frequency spectrum, okay? Each has its window. Okay, so now we want to do really the weighted sum. So it means that we send two signals together, two inputs, okay? So here are two inputs, are power 1 and power 2. Each are carried, and this is very important, by a signal of different frequency. We sum them together, okay? And then we send the two signals together into the chain of the two devices in series, okay? And so each synapse will respond to one frequency, okay? We choose this frequency so that they match the frequency of the synapse. And so what you will get as a voltage across the chain is really this weighted sum of the two inputs by the two synaptic weights, okay? And so what is nice is that then with this technique that we call frequency multiplexing, you can have a dense connectivity with a simple architecture, because you see here, if I have now two output neurons in the other layer, so if I want to connect these two to two things, you see I can sum the signal again, and then I have several chains, and I can send the same signal to all chains, and they all will perform the weighted sum, and I just have to tune each frequency of each synapse to have the weights. So basically what you can do is take all the outputs of the neurons in one layer, sum them all together, and send all of this to the synapses, and every synapses will rectify the correct signal. Okay? This is a crude view of how it works. I will give a bit more nuance later, but I think this is the good way to understand it intuitively. Okay, and so we did the experiment of this, so where we send the two signals together, and we get indeed this weighted sum, and you see this is what we measure, and this black line is the ideal thing we would want to measure, and you see that we have a pretty good agreement. Okay. Okay, so now we have our synapses. Now let's see what neurons can address them. Okay, so as I have told you, we use the same device, again a magnetic tunnel junction, but this time, instead of injecting RF and getting DC, we do the opposite, okay? So we inject a DC current, and we will get an RF emission. So because this is just the spin torque oscillators that I think many of you know. And so we have a spectrum like this at a well-defined frequency. And if we plot the RF power versus the input, so the DC current, what you see is that we are at 0, below a threshold, and then the threshold, when we are above a threshold, we can excite these auto oscillations, and we get some power increase. So you see, this is our nonlinear activation function, okay? But we have a small issue, is that you see, if we look at the frequency, it varies as well with the current. And this is not good, because I have shown you my synapses, they work when I send them an RF signal at fixed frequency, okay? So this was the problem, and so we fixed it So what we did was also to have a strip line above the device. And again, you can change the frequency of a device by sending a DC current. So you can counterbalance the frequency shift due to the input. Okay, and so you see indeed here, when we use this trick, the frequency now doesn't vary with the input current. We managed to fix the frequency. And again, this is not something that we would want to do in the final system, because this consumes energy. So we would like to have oscillators where like the frequency of oscillation does not depend on the output power, does not depend on the input. And so it would be oscillators like the one that were shown in this paper, okay, if you guys know it. So yes, again, today I show you this trick, but this is the path to go towards something that's more viable for a real system. Okay, so now I have synapses, I have neurons, and I will now put them together to do a fully spintronic neural network. So first thing I'm going to do is to connect one neuron to one synapse. Okay, so here I prepare you the schematic for when there are two neurons and two synapses, but here only one neuron is active, so okay, this one we send 0, so only this one is emitting, and it will go to a chain, but because there's only one on, it will only address one synapse. So what you see is that I measure the voltage across the chain, across the synapse, versus the input to the neuron, okay? And what we see is that we get this activation function again, the nonlinear activation function of the neuron. And if I change the frequency of the synapse, I change the weight. And you see that we get indeed this cascade of operation where you have the activation functions times a synaptic weight, okay? So this we were really happy because it was really the first time we were able to connect a nanoneuron to a nanosynapse. And I think the reason that it works so well is because what comes out of the spintronic nanoneuron is this beautiful RF signal with a nice quality. So you can indeed, we didn't see that much difference between when we measured with an RF source and when we measured with RF coming from the nanoneuron, okay? Of course, the nanoneuron doesn't give an RF signal that is as perfect, but for this application, it is completely sufficient. It's really clean enough, reproducible enough that we can use it, and you still have this beautiful like linear slopes, okay? So this we are really happy about. Now we add the other neurons, and so basically, it is a bit the same thing. So now not only you have this nonlinear activation function, but you see that if we turn on the other neuron, you can now add the component due to the other neuron. And okay, so I could show you many plots like this. If you're interested, you can come see me later to see all the data. But basically, you can tune with these two inputs, and you can really see that we get the expected function, which is that the output voltage is a weighted sum. So this time, not just of RF inputs, but of RF inputs that come from the neurons. So these are the activation function, and they are multiplied by the weight and then summed together. So this was really the first experimental demonstration, to our knowledge, to a layer of nanoneurons that connect to a layer of nanosynapse. And for us, that was really the crux of the thing that allowed us to have now a scale, like a modular system. So this, this took 2 years to get to find really the right devices and understand how to control them and have this nice behavior. But this was really the key result. And then using this, we can build a small neural network. So I thought of what is the smallest neural network I can demonstrate, and it is this. So you have two inputs, okay, and then they go to two neurons, and because these neurons are not input or output, we call them hidden, just how we call them in the field. So two hidden neurons, and then it goes to one output neuron. So you see here, we have 2 inputs connected to 2 neurons, so it means 4 synapses. So they are here, so you have 2 inputs, and you have 2 chains of synapses, 2 chains of 2 synapses. Then you have 2 neurons here, okay? And then you have 2 synapses and the output neuron. So you see really the devices are the same, the neurons and synapses. And so what you need here, so you need this DC voltage converted to a DC current. And so this we just measured from the voltmeter and injected with the source current. So here we were going through the computer. But so in a real system, and so now we are building a CMOS integrated chip where with the MTJ and the CMOS, so we do this. So you need a DC amplifier, which is something that people who design CMOS can do, but us, we didn't want to do this for the tabletop demonstration. And so, but this part, where you have the neurons that feed into the synapses, really this was done in just one fully experimental step. And then you have this output neuron. So you see 2 inputs, send them together, send all to the synapses, send to the neurons, send their signal together, send to the synapse, send to the neuron. Okay? And so we wanted to demonstrate that the hidden layer of neurons, so that this part basically, which was the experimental crux, but this was doing something significant. And so the way that we demonstrate this is by showing a task that is small but is nonlinear. So nonlinear means that you cannot linearly separate the inputs. So here I have 2 inputs, okay, power 1, power 2. So let's see here, for instance, well, let's take this example, for example. You have power 1 and power 2. And my task is that a task is the boundary, so this black line. And I say now, you need to put all inputs in one side to be red, all inputs in another side to be blue, okay? And why is it nonlinear? Because this line, the line of the task, is not a line yet. Well, it's I shouldn't have called it a line, sorry. The shape is not a linear line, okay? You see? So if it was a linear network, all we could do is separation by one line like this or like this or like this anyways, but not something that is nonlinear like this. So to have this nonlinear shape, you need to have a hidden layer, okay? And so you see we show different tasks. So here are 3 examples. You see each of them are nonlinear. So, okay, in the simulation they are perfect because these are not hard tasks, they are just nonlinear. And you see the experiment does quite good as well. So here, for instance, we have 1 missing point. I think here is perfect. Here there's 2 missing points. So you see we really have around, like, I think in total this was 98% accuracy over all the tasks we tried. So we were really happy because this means that the network is able to do this nonlinear task. And so just a note that sometimes it's hard to know which neural network tasks are hard or not. For instance, the task digits that I will show you later, that is recognizing hand authentic condition, you can get actually almost 100% with just a linearly separable thing. So sometimes tasks are impressive because they are big, the input is large, but actually they are easy to do for the neural network, while this is a task that is very small but not that easy because it's nonlinear. Okay, so this was the experimental demonstration of our nonlinear classification. And now, to show you different tasks, we have performed simulations. So the way we do this is that we use this library based in Python called PyTorch that's widely used in machine learning. And this library allows you to define custom functions for your neurons and synapses or for your whole system. And then it allows you to train it through backpropagation. So this is an extremely powerful tool to do research in machine learning and neuromorphic computing. And so we can put the physical models in the device, in the simulation. And so here, again, it is really nice that we have these spintronic devices that we can model very accurately. Because in other subfields of neuromorphic computing, like with memory devices, the models are not as predictive. And so really in spintronics, the ability to understand what goes on in the device, to model it accurately and put it in the simulation is really a huge advantage that we have. Okay, so first I show you this simple task called digits. So these are handwritten digits. You see 8 by 8 pixels. So each image is converted into a vector input. So each pixel now is an RF power, okay? These codes are inputs. Each of them has a different frequency. We sum everyone, and we send them to 10 chains. So why 10 chains? Because we have 10 classes, 10 digits. So we have 64 by 10. And we look, when we do the training, and we look at which chain has the highest voltage. This means this output is the class that the neural network predicts. And you see here, we do the training, and after we train, so here, one epoch is when you show the whole data set, and you see after a few tens of epochs, we get a high success rate, so we classify almost perfectly the data set. And you see that we classify the spintronic simulated network classifies as well as the conventional software neural network. Okay? So this is very nice. This is just an example to show you what a chain would look like when you have many devices. You see we have all these resonances, okay? But this is just an easy task, as I have told you, because it's linear, you see. There's no neurons here, only synapses, and it already classifies almost 100%. So we have simulated larger architectures. So for instance, a large network with one hidden layer. So this is basically like the experiment, but with more neurons. And so we're able to do MNIST, which is a task that's similar to digits, but larger, 28 by 28 pixels images. And you see, again, we do as well as the software neural network. And also, we have developed an adaptation or architecture to go towards convolutions. So I don't have time to get into this today, but basically convolutions are a special type of connectivity that it does like filters. You have these convolutional kernels. Basically, it's like applying filters to your image to extract important information, and the filters are learned by the network. That's why it's so powerful. And so this is really what is used in state-of-the-art neural network, especially for image and video recognition. And so we have developed an architecture for this. And when we do simulation, we see that again, you see here in red is the spintronic and blue is the software. We do as well as the software network. So we show that we can really scale up this task. And one application that is not something so famous, but I think it's very interesting for our system, is a radio frequency application. Because remember, our synapses can take RF signals directly, okay? So side note, if we want to have DC signals coming in, we can just start by a layer of neurons and they take DC. So this is not a problem. But I think that the ability to take in radio frequency signals directly is really something that can be super interesting for applications. And okay, I work at Thales, so we love a lot of applications with radio frequency signals. And so what is nice here is that normally, if you want to do some kind of analysis of a radio frequency signal, you need to take the radio frequency signal, you shift its frequency to a lower frequency with a local oscillator, then you digitize it, then you do some operations on something. So it costs a lot of energy and time, and it's complicated. And I think that now, with our nano devices that are directly radio frequency, really by leveraging this RF dynamics, we can take the input, RF analytic input, directly, put it directly after an antenna into the synapses. So here, I show you this task where you have signals coming from drones, so commercial drones, you know, these toys that you can buy, and you send the RF signal to our network, and it tells you which drone it is. So here you have examples from the 10 classes. And you see that again, we can really recognize with, I think it was like 98% accuracy, and we do as well as the software. So this opens a lot of applications, and I think also, because I don't think everything should be about application. I think here it's also something really nice about by using the physics of the device, we are not just doing, okay, like neural networks, but at lower cost, but we're also really using the physics to go beyond. And so I think this is very interesting. Okay, so small comparison to other technologies. So as I have told you, what is really, I think, the main improvement here is that we have managed to do this modular architecture where you can stack layers. We have really achieved to take nanosynapses, feed into nanoneurons, feed into nanosynapses, and so on. And so we have this alternating layer, so alternating RF and DC. So it's really key that each layer goes back to DC. This way you don't have one big complicated network where everything is RF, okay? At each layer you regenerate the DC, so each layer is completely modular, okay? And it's very nice also that we have the same device for neurons and synapses, because this will make the co-integration easier. Okay. And we think that this frequency multiplexing technique really helps you improve the connectivity. Because you see, here you can, so as I told you, you take all the signals from one layer and you send it to all synapses. And you see these are separate chains. So you might have some inaccuracies that come from things going on in one chain, and we can discuss this later. But you will not have issues going from one chain to another. So this means that you don't have inaccuracies going from one output neuron to another output neuron. While when you have these crossbar arrays of memory devices, this is something that you do get with sneak pass for those who are familiar with it. We can discuss more about this later. But so we think that really this simplifies the architecture to go to higher connectivity. And so yes, so a question that I often get is about how you can, how many synapses can you put together and things like this. So of course, these are still questions that are quite open because we have not yet demonstrated large chains. The best I have done is 4, so it's quite small. But one thing I want to point out is that I have given you this really simple picture of like, oh, one signal address one device and they each have their little zone and things like this. Obviously, if you want to do it like this, it reduces the number of devices that you can put on a chain. However, you thankfully do not have it to do it in this cartoonish way. So actually in our simulations, we pack many synapses on one chain. And so when we did the MNIS, for instance, you have really almost 800 synapses on a chain. So 800 neurons connected to 800 other neurons. And so the devices overlap. So this is one example of overlapping. You see, when you send here, for instance, one input, it will address one device, but also the other devices that are next to it. Okay? So we take this into account in our simulations, and it doesn't stop the system from working. Basically, it just means that the synaptic weight is not coded just by one device, but by several devices, which is not a problem for the system to learn. What we do see is that, indeed, if you really try to pack too much in a small frequency zone, you start to have some issues for learning. And the reason for that is that I have told you, remember, it's extremely important that every connection can be tuned individually. And the thing is that if you have really many devices close together, then it means that the input signals that you send are also very similar. So let's say that I'm sending 2 inputs, and they are at really close frequency. So this means that the way the chain will respond to both will be quite similar. It will be very hard to tune the system in a way that these 2 signals that are extremely close react in a way that you can tune independently. And this is what limits the number of what we can put. But I think already having these hundreds of devices in one chain will bring a huge improvement in the connectivity. And so this is to illustrate what I just explained you. You see, these are weight value by input neuron. So each color is one output neuron. So let's look at one color, for instance, like this light blue. You see, so each point is one weight, and you see they seem quite random, okay? Because they have been independently learned. And if I have now my syntronic neural network, and I give a large range of frequency for my synapses, so here it was 20 gigahertz, you see, again, they are quite random. We can tune them independently. But now, if I try to do it with just a few 100 megahertz of range, so if I try to put these hundreds of synapses in just this small frequency range, you see now the weights are correlated. They are not independently tunable anymore, okay? So this is to answer these questions about how much you can pack. Okay, and for the energy consumption, so of course, you know that these estimates are very hard to make, and it's, you can really fall into being over-optimistic or over-pessimistic, depending on how you feel that day. So what we have done is really try to work with the people who are designing the CMOS for our chip, and really see, okay, what will consume energy in the final system? So really trying to think about the whole architecture and not just device by device. And so what consumes energy in the system? It's this RF amplifier that will take all the inputs from one layer, all the signal from one layer, sum them to send to the synapses, and also these DC amplifiers that take the voltage out of a chain and convert them into current to feed the neurons, okay? And so by looking at how we can build these circuits and how much they will consume, we make the estimate that we'll have approximately 10 femtojoule per synaptic operation and 100 femtojoule for neurons. And this is with an assumption of MTJs that have 20 nanometers of diameter. So this is actually a consumption that's pretty much the same as other nano neurons and nanosynapses technology. So we think that here we are competitive, but this is not our big advantage. The big advantage is more about the architecture and things like this. Okay, so now in the few minutes that I have left before, perfect. I just want to give you one last challenge to think about, which is at least what I think about. It is how you train this system, okay? So first thing I want to emphasize that you need to train your system. So of course, what you could do is say, okay, I'm going to use this backpropagation on a computer to train the system. So what I have done in my simulations, basically, you train it and then you put the weights into the system and you use the system just for inference. That's fine, okay? So if you want to do this, you're fine. But I think that it really limits what you can do because then your system cannot be retrained, your system cannot adapt in time. And I think also it's not where emerging devices will be the most competitive because now CMOS-based accelerators that are just for inference are being extremely good. And it's really not clear that emerging devices have something to bring for inference only. But for learning, I think we have a lot to bring. And the good news is I think that is also the most interesting because I think this is where the physics of the devices will have something to bring. And I will get to this in the next slide. And so really emphasize, so learning is necessary, I think, and you need to learn. I also want to point out that the approaches where you don't really train your network, for instance, like the reservoir or extreme learning, sadly, they do not scale. So they are amazing at a benchmark test for the system, but they cannot be the end goal. You really need to think about how you're going to train your devices, your system. Okay, but the thing is that it's very hard to have a system that you can keep training on chip, okay? Why? Because the way that we have to train neural networks now is called backpropagation, and it's not hardware friendly. So I will explain you why. So let's say we have a neural network and we want to train it. So we have our network that does the inference part, so-called forward. So it means input go through neurons and synapses and you get your output, okay? Now, if you wanted to do the training, what you need is to have a second circuit on your chip that computes the gradient backward, okay? And store them so that then you can have a third circuit that programs your synapses, okay? knowing that for backpropagation, often the increments of the weight updates are very small, so it's hard to do with emerging devices. So it is really a big challenge to build a circuit on chip that can do this training. And really, it seems that this backpropagation is not adapted to hardware. It's not hardware friendly. So on the other side of this, we have alternative training algorithms that are more inspired from neuroscience or physics. So I think we will see some great talks in the rest of the session using all these energy minimization techniques and things like this. So this is more like physics-inspired learning. And so you have all these methods, but the issue is that when it comes to neural network, they tend to not scale very well. For instance, you see here, you have accuracy on different tasks, so MNIST, which is quite small, and then larger tasks. And you see in black, it's backpropagation. The accuracy stays quite high. And then if you have these two others, so STDP is something with spiking neurons, feedback alignment is another method, so these are more like neuroscience inspired, and they do not scale. So this is really a bit of a sad thing that on one side we have this method that works super well in state of the art, but it's not hardware friendly. And biologists say that it's not possible that it's done exactly like this in the brain. And on the other side, you have these rules inspired from neuroscience that are really hardware friendly. They have a lot of nice property, we can discuss it later, but they don't really scale to state-of-the-art tasks. And so it's really a hot topic in the machine learning and computational neuroscience of how you can try to merge the two to take advantage of both. And if you're interested in that, I encourage you to read this review paper and also to watch this video of Hinton where he explained how the brain might be doing some kind of approximation of backpropagation. So this is really open-ended question. And so really the big goal will have to be a physical neural network that can do self-learning, which means it learns by its physics and not because another circuit has on the side explicitly computed the learning and told it to do so. So this is really something that's open-ended, but I think that this is a fascinating topic, and I think that this is really some place where we, as physicists, have something to bring, because this is really about leveraging the dynamics to do something beyond what standard static AI neural network can do. So this is really exciting, but completely open-ended question. So this is the conclusion of my talk. To sum up, we have realized the first experimental demonstration of communication between several layers of nanoneurons and nanosynapses, and we have performed a nonlinear task with high accuracy. And I have shown you by simulation that we can go to larger tasks and do these native RF applications. So the next steps are to scale up the system by building this co-integrated CMOS MTJ chip, okay, and also to implement this self-learning using the dynamics of devices. And so I hope I have convinced you that these spintronic devices are really key technology for the self-learning system that we're trying to build. And so if you're interested yourself, you can maybe join the team. And if you're too old to join the team, and if you already have a great position somewhere later, maybe you can send us a student or something. So we're hiring, we have several positions open, so please come see me if you have good people to recommend or yourself. Thank you.